Hello, my name is Brent Walker, and for my physics project, I did the physics of scuba diving. Scuba, or self-contained underwater breathing apparatus, is a recreational sport that is based on many pressure-related standards of physics. I have learned that these standards are necessary to keep someone alive and mobile in an unnatural, high-pressure, underwater environment. During my time earning my certification in scuba diving, it has taught me many things that involve physics in scuba diving, such as pressure, buoyancy, sound, light, and thermal insulation, that all play a key role in being able to explore the underwater world. Pressure must be understood first over everything else in scuba diving. This is the borderline for humans to overcome in order to breathe underwater. The properties of water thus can help with that factor. One must first understand that water is much denser than air. This means that water has more mass per unit volume than air and will weigh more unit volume as well. Water is also uncompressible, which means that water under great pressure, force per area, will have the same volume as water under much less pressure. Taking in this information, the first notable sign one can feel of this underwater pressure would be when someone dives to the bottom of a pool. When they reach the bottom, they may feel pressure enclosing on their ears. This feeling can easily be understood as the water above them pressing down on them and thus squeezing the air inside their ears into a smaller volume. In scuba diving, the high density water all around the diver will press in on them from all sides and will increase as they go deeper. For example, a diver would not be able to breathe through a hose at the surface while they're down or deep down in the water, as their lungs would need to push all that water weight outwards to make room for the air. So we look to scuba to help solve that problem. When the diver breathes from a scuba tank, they breathe air at the same pressure as the surrounding water. This means that, although the water presses in on you, the air you breathe presses back out with the same force. Essentially, that equalizes breathing at any given pressure as long as the diver continues to breathe without hesitation, which is the #1 rule in scuba diving. And as you can see in this picture here, this is a picture of a diver trying to equalize as he goes down by holding his nose and pushing air from the nose into the sinuses that will push against the pressure on the ears to equalize. Secondly, there are a lot of physics behind buoyancy in scuba diving. Buoyancy is what determines whether an object will float or sink when it is put into water. Something that is less dense than water will float, while something denser will sink. The density of an object can be obtained by taking that object's mass and dividing it by its volume. When a scuba diver goes underwater, they want to reach neutral buoyancy, because positive buoyancy means floating and negative buoyancy means sinking. The happy median of neutral means that they are neither sinking nor floating, which makes it optimal for the diver. As you can see in this picture, they've reached the balance between floating and sinking. A diver will have a natural tendency to float, so they use a couple of compensators to counteract that problem. Using weights on a weight belt is one example of stabilizing the diver for neutral buoyancy. The other is the buoyancy compensator, or BC for short, which is kind of like a life vest for divers, in that they can add air if needed to help make them more buoyant. The more popular choice these days to avoid hassle is weight-integrated BCs, which eliminate much of the hassle of having a weight belt. Without the physics of neutral buoyancy, a diver will either float back to the top or sink to the bottom and damage things like fragile coral reefs in the process, and that would be bad. And here is another picture of an example of buoyancy. See, in #1, the diver is negatively buoyant. When he inhales air from the scuba tank, it lifts him up. When he exhales, the air that's in his lungs, he will go down. If you can control your lungs from going up and down with the regulating breathing, you can meet the happy medium of neutral buoyancy, which is shown in number 4. Being underwater, we often think that sound travels at the same rate it does at the surface. This is a common misconception, and physics can tell us why. Sound travel is completely determined by the density of material it travels through. The denser the material, the faster it actually travels through it. As stated earlier, water is much denser than air, so sound travels much faster underwater, about 4 times as much, compared to the surface. I have realized firsthand that this changes our ability to determine the origins of sound underwater. When I am at the surface, I can figure out where a sound is coming from because there is more of a time delay of it reaching my ears than, than that of being underwater. When we are underwater, the sound travels so fast that our brains can't figure out where the sound is coming from. Above water, a blindfolded person could determine the direction of sound at 10 degrees, which is not possible for a scuba diver. Before I learned to scuba dive, I was always curious as to why nobody but me could hear myself yell underwater in a place such as a swimming pool. This is because the sound vibrations do not transfer from air to water very well. As divers, we get each other's attention by hitting our tanks with a plastic ball that wraps around the tank with a bungee-like loop that makes a clanking noise. This works because when metal vibrates, the vibrations are transferred directly to the water and can be clearly heard, even if its direction cannot be determined. Knowing this, I was taught to think completely different about sound underwater during my certification course. Okay, light. Light is also an important factor in the physics of scuba diving. When I'm underwater, I can't rely on my eyes to be as accurate as they are on the surface. If I were to look at the surface while underwater, any object I see up there would be in the wrong place. This is due to our eyes automatically assuming that the light reaching them is traveling along a straight path. This phenomena is due to the fact that light travels slower in water than it does in air, which is similar to sound traveling faster in water. Because of this, light will appear to be bent when it hits the water. I also learned that when I look up while on a dive, I can see a limited amount of the surface which looks wavy and interesting at the same time. There is a critical angle for this at which light is either internally reflected or passed through bent at 49 degrees from water into air. Initially, the diver underwater will be unable to see anything that is less than 49 degrees above the horizon. When diving with a mask, it causes objects underwater to be 30% larger than they really are because of light bending through the lens. Another important factor about light to take in consideration while scuba diving is that colors will begin to drop out at varying depths as you dive down. To speak more specifically, red is the first color to disappear at about 30 feet underwater because it has a longer wavelength than other colors. As the colors fade, it is noted that only blues and greens are left at depths below 100 feet. This is why many divers use flashlights, which allow them to see other colors. And here is kind of a picture of the loss of coloration example. As you can see, I mean, this is at the surface that you can see all the colors perfectly. And then you start to go descend underwater and you see the colors start to fade. Red starting out first, starting to get darker. And then you get down to about 10 meters and you can see you can't really see red anymore. You can just see like yellow, green, blue. That's about it. And then you get down to 20 meters and then even the reddish orange is gone and you can barely see yellow and green. But blue, or well, green and blue are more prominent than that of yellow and red and orange. Finally, thermal insulation is a big part in the physics of my body when scuba diving. Oftentimes when breathing dry, compressed air, I would feel cold over time while wearing just a swimsuit. Wearing a wet or a dry suit is key in keeping the body warm when being underwater for an extended period of time. These pieces of swimwear function through the physics of thermal insulation. Simply put, thermal insulators are used to minimize the transfer of heat energy. They are meant to keep something from becoming the same temperature as the surrounding environment, which will keep someone from becoming as cold as the water while scuba diving. As someone dives, the type of heat transfer that makes them cold is called conduction. The water is in direct contact with our skin, so the flows from our body into the water. When using a wetsuit, it traps the water within the suit because water is the best insulator next to air. A dry suit uses a layer of rubber and a layer of air to keep the diver warm. This is the best thing to use in cold water environments to insulate the diver. And here's kind of a picture of someone who is cold and doesn't have enough layers to keep themselves warm. They're not using a dry suit, they're just using a regular suit that traps water in the inside and prevents the heat energy loss. So, in conclusion, there are many aspects of physics in scuba diving. All of these factors must be taken into account for one to understand the many wonders of scuba diving. The pressure of water has a whole different effect on us than the outside air because of how much denser the water is than the air, which is the main point of each factor that needs to be considered underwater. To be able to traverse this environment, we must be able to adapt to those physical factors, such as buoyancy, sound, light, and thermal insulation. Understanding the physics of diving is understanding the underwater world.